Okay. Hello everybody. So my name is Geert Uiterhoeven. I started programming a long time ago as a hobbyist on the Commodore line of home computers. Then about 25 years ago I learned about Linux, and a bit later I started contributing to Linux by supporting the port to the Amiga with the M68K processor. Later I ported Linux to the Common Hardware Reference platform, which had a PowerPC processor. And for a while I was Linux firmware for device maintainer. In the meantime I started working for Sony, and while at Sony I started working on Linux for the PlayStation 3 game computer with the cell processor. It was a really fun time. And a few years ago I became a freelance embedded Linux kernel hacker, and since then I've mostly been doing upstream Linux work for Renesa's ARM-based SoCs. Something, it seems the titles are not on the screen, but so something about me and FOSDEM. So in 2000 I heard about this interesting new small conference here in Brussels called FOSDEM, so I decided to attend it. It was great. Next year there was FOSDEM, greater and greater and greater. And since 2004 I've been a member of the program committee for the embedded track, and I've kept on attending FOSDEM until now. But I've been presenting at many other conferences, but actually this is the first time I'm presenting at FOSDEM, so welcome to Linux as an SPI slave. So about 3 years ago, Linux got support for I2C slave support. And then people started wondering, could we have SPI slave support as well, where Linux is doing the slave part of the SPI side and not the master side? And yeah, the answer is yes, but. So, and in this presentation I will tell you what is possible, why it was that difficult, what's different about SPI compared to other buses. So let's start with the basic SPI bus. It's a bit annoying that the titles are not there, but okay, we can handle. So SPI, it started as, it was developed by Motorola in the 80s to control different simple peripherals from a microcontroller without using too many wires. So it's a bus, and you have a data outline from the master to the slave called master out, slave in. You have a data inline going from slaves to the master. There's a clock line controlled by the master, and there are one or more shift selects to select the individual slaves. So basically it's just a glorified shift register. So the hardware is actually quite simple. Important to notice is that it's the master who's in charge, and that there can be multiple slaves. And the master is in control, and we have simultaneous transmit from master to slave and receive from slave to master. And speeds can actually be fairly high. They go from the tens of kilohertz to a few tens of megahertz. So a sample SPI transfer is shown here. So at the top we have the line with the data going from master to slave. Below that from slave to master. Then the clock signal and the chip select. So when the chip select is selected by the master, a bit later it starts clocking, and then data goes out from master to slave and goes in from slave to master. This is really low-level hardware, and of course low-level hardware can be done in many different ways, so there are lots of options. Do we sample data lines at the rising edges or falling edges of clocks? What's the polarity of the clock? Chip select polarities, they can also be active high or active low. Which bit do we transfer first? And in this case has to be taken into account. As it is low hardware and not always used for 8-bit systems, you can have different bits of words. 8 and 16 are fairly simple to handle, but sometimes you can have 12-bit words, something like that. And one important parameter, of course, is the transfer speed. You should transfer data not faster than the slave can handle. There are also a few simplifications possible. Not all SPI systems implement the same thing. Some slaves you can only write to, so they do not connect the master in slave out lines. An example is an analog to digital to analog converter. You can have slaves where you just want to read data like a sensor, so you don't have to connect the other wire. There are also slaves where they combine the data in and data out lines, so it becomes a half duplex protocol. And if there's only one slave, you don't need a chip selector. That's an even further simplification. Besides simplifications, there are also extensions. So people wanted higher speeds, so they thought maybe we can combine the two data lines to transfer 2 bits of data from master to slave or from slave to master. Obviously, it becomes half duplex then. Later, that was extended to quad SPI, where you add 2 extra wires, and then you can transfer 4 bits of data at the same time. This is typically used for SPI flashes. Another way to make it even faster is to add double data rate support, so you sample the data at the rising and the falling edge of the clock. I don't think so far Linux SPI supports that. Maybe in some specialized SPI flash controllers that show up as MTD device and not as SPI. Probably they do. And then recently we've been seeing systems where they just add 2 QSPI flashes and address them in parallel, and then you have 8 bits of data. And sometimes that's also called hyperflash. And that's even faster. So this is about the SPI protocol. So an actual SPI message in a protocol consists of several transfers. And each transfer is can be a half duplex or full duplex. It can be a single transfer or a dual and a quad. You can have some dummy cycles to give the slave some time to calculate some data or something like that. But that's all highly slave device specific, and it's dictated by the protocol. And typically, yes, the chip select is asserted for the whole message usually. An example for that is a simple SPI flash read. So it consists of 2 transfers. As you can see here, the chip select is asserted for the whole message. And this is the first transfer. Here we have the second transfer. The first transfer sends a command for this particular SPI flash 3 means read data. Then the 2A is the offset where to read in memory. You see that the data is transferred from the master to the slave. And in the second part of the transfer, data goes from the slave to the master, and that's actually the data that you read from the SPI flash. So far the simple basic SPI. Now, if you want to have support for SPI slave in Linux, there are a few challenges. So the biggest one is basically that you have simultaneous transmit and receive, and that the master has control. So the master controls the chip select, the master controls the clocking, the slave has to follow data. So it's a real hard real-time system. That also means that if the master requests you to send data, that you must have already written the data on the slave side in the transmit FIFO. It also means that if the master sends a command, for example, reading from a flash, that the response has to be prepared before by the slave, if it's software-based. So that means that if you want to do software SPI slave, that the slave response cannot be a reply to a command in the exact same SPI message. So if we want to do that, then we need the SPI protocol where the slave response will be in the next message. So how did I start working on this? So as I told you before, I'm doing contract work for Renesas, and then one day they asked me, can you please upstream SPI slave support? Well, we have it for I2C. Why? Well, we have it for SPI. I had my doubts about that. But yeah, then we actually had something. So inside the Renesas RCAR BSP, there was code to support that. So you probably know a BSP, that's a board support package. It's an old or not so old Linux kernel source tree with lots of patches on top that add, change, remove, break various levels of functionality. So usually the code is not ready for upstream. But yeah, there was something. Then I asked, so what kind of use case do you have for this SPI slave implementation? Because there are many challenges. And up till now, I didn't manage to get out the real use case there. So most probably they're using SPI dev from user space. But We don't really know why. But the important part here was that the customers from Renesas, they were happy with the implementation, so it must do something. So who am I to say that, that it cannot be done? So I decided, yeah, okay, let's do it. Create my own use case there, get it working, and then make the code fit for upstreaming, make the required changes to have it nicely fit into the existing Linux SPI subsystem. Yeah, to find a good use case and to overcome the challenges, I like to compare the SPI bus with a few other buses where we do have some kind of slave support in the kernel. The first example is I2C. I'm not going into all detail, but most information is on the slides, which you can download later. So on I2C, we did get slave support a few years ago. And the major reason why that's workable is that on I2C, the clocking is also controlled by the master, but it's an open drain signal. And the slave can actually, if the master asserts the clock and the slave is not yet ready, the slave can also assert the clock. So because it's open drain, it will stay asserted, and that's called clock scratching. So during that mechanism, the slave can delay everything until it's really ready. Another bus is the UART bus, the serial standard serial port. Yeah, if you're on the receiving side of as a UART, then yeah, your receive buffer can overflow. But apart from that, there are not that such big issues because, unlike for SPI, the other side controls itself when it wants to transmit something, so it can wait until it's ready. So the both channels are. Both bidirectional channels are really separate. And optionally, you have a hardware flow control like request to send, clear to send, which makes it easier. A third bus I looked at was, yeah, it's really a shame that the titles are not visible, is Ethernet, yes. So Ethernet, it's used to be half duplex. These days with switches, it's full duplex. But again, here, each side controls its own when it's ready to transmit something. And on top of that, Ethernet is usually used for network transmissions. If packets are dropped or lost, the driver can drop them, and the upper layers will usually handle it fine later. This is about USB. So in USB, everything is basically controlled by the master, but the master pulls the bus, and then there are also packets and the acknowledgements. So it's quite complex, but basically it means that there's no real issue with slave data getting lost. The last one is one wire. That's not so interesting here because we don't have one wire slave support in Linux. I think it's more or less similar like SPI if you want to implement it, but that's still something to be done. So this is a summary of all the things that we have in the various buses I went over that make it simpler to design a slave protocol later. Things like hardware flow control and upper layers handling retransmissions could be interesting if you want to design your own SPI slave control. So what kind of use cases can we have with SPI slave that are definitely possible to implement? One of them is just the master sending data to a slave, no data going from slave to master. So as long as you don't overflow the receive FIFO, everything should work. So if the speeds, you don't go to too high speeds, you can get it working. You could add flow control. Another thing is reading data from the slave to the master. There the issue is when do you know when the slave has data to send. Could also be handled by polling. Bidirectional is a combination of both. There you have to consider that the response can never be replied to a command in the same message. A nice example of an existing SPI protocol that shows all these limitations is in the Nordic Semiconductor NRF 8001 Bluetooth low energy controller. They basically show what you have to do there, and in that system, they don't really use a chip select, but use two separate signals. There's a master request, which is basically some kind of chip select, and a slave ready. So when the master wants to send something, he asserts the master request. When the slave is ready to accept the data, he asserts the slave ready. Then the master sends commands, which are always first a length byte followed for some data. At the same time, it reads data from the slave, which also starts with a length byte followed by data. If the length is 0, the slave doesn't have to say anything. Now, if the slave has some information to send to the master, it will assert the slave ready signal first. After that, the master will assert a master request, send a dummy command, and read the event from the slave. So, and the datasheet there states explicitly that the event is is received from the master is never a reply to the command from the master to the slave. So yeah, what we definitely can do is receive streams of data with simple messages, but I don't go into detail because we're already running a bit out of time. So when Linux gained I2C slave support, the first example that Wolfram Zhang wrote there was an EEPROM simulator. So with I2C that worked because you have clock scratching. For SPI, it's more complicated, so I was wondering whether we could do something similar. But if you look at all the various SPI slave drivers that there are in Linux, there was not really anything that I found interesting. I would have loved to write a SPI slave Ethernet driver that you could just connect another Linux system over SPI and it would behave like a fake network interface. But all the SPI Ethernet drivers, they use protocols where the response to a command is part of the same message, so you could not do that for the slave. So I had to come up with something myself, and one example was that you can query the system uptime of a system, and another one is that you can send some commands to a system for remote control, like suspend and reboot. And of course, you can use SPI there. So this brings us to the actual implementation. So there were first steps to be done. The first one was to get device tree bindings in, extend the SPI subsystems to support for slaves, extend one of the existing Renesas SPI master drivers to support slave, and then some example SPI slave handlers. Device tree bindings, this is a sample for a normal SPI bus with the master controller. So you have the device node for the master, then you have a bus with one or more devices. In this case, it's a PMIC. And that's how it is described for master controller. So for a slave controller, we just add a SPI slave property and a single subnode without a unit address and without a register representing the slave. The compatible value here specifies what protocol is used. That subnode is optional. We also made it that you can configure it from user space later. The subsystem changes. SPI slave support is completely optional to a new kconfig signal. There's a new SPI class device was added and a mechanism to bind the slave protocol to the actual slave controller. So as I said, there are two ways. One of them was a compatible value in DT, which is optional, and the second one is to write a value of the driver identifier to a virtual file in sysfs. The subsystem also gained 3 new API calls. Instead of allocating a master controller, you now can allocate a slave controller. The second one is because I told you before that the slave has to prepare data to be received by the master before it receives the master request. So suppose that you have already prepared the data and then you want to unload the driver or something like that, you have to abort that operation, so a new API call for that is added. And the third one is just a simple check to check whether the controller is master and slave, and it takes into account the configuration options, so for drivers that support both master and slave. And as a last step, we generalized that the current SPI master naming was changed to controller because everything stayed the same, but master was not a good name for that anymore. And that's actually the largest part of the patch set. So how does a SPI master driver looks like. Oops, forgot this one. This is a very simple one. You create a SPI master structure, you fill in capabilities, a few callbacks, and you register it, and that's it. What needs to be changed for a slave controller? Instead of SPI master, we now have SPI controller, which is basically just exact the same thing. You call alloc slave instead of alloc masker, take care of the new callback, register everything, and that's it. Now the changes that had to be made to the Renesas SPI master driver, they were actually quite small. So the low-level core of that was based on the sample patch we had in the BSP. So from the hardware point of view, it's actually quite simple. You just consider the clock an input instead of an output, and the rest of the hardware will handle it fine. On top of that are the more complex things. You have to register as a master or a slave controller based on the DT SPI slave property, whether it's present or not. When writing hardware drivers, you typically program the hardware to do something, and then you wait for an interrupt to happen that will trigger completion. For a master controller driver, it's something waiting for completion with a very short timeout, just in case the hardware hangs. For a slave controller, you never know when the master's gonna send you a command. Could be in 1 second, could be in 1 hour, so you have to use a different wait for completion call, and one that can be aborted through the slave abort callback. And with the current Renesas MSIOF driver, there's a limitation that the message size must be known in advance. I think that can be relaxed because the hardware does know when the ship select is no longer asserted and when the message is ended, but that hasn't been implemented yet. Now the final part is the SPI slave handlers. So the existing SPI slave drivers in the kernel, they all assume that they're talking to a slave device through a master controller. So the new SPI slave handlers, they are used to listen to requests from a remote master. We managed to keep most of the existing infrastructure as is, so everything can be reused as much as possible. SPI slave handler uses almost the same API. The only differences is that when you send data to the master, it will not be sent immediately, but only when the master requests for it, and you can abort it when you want to unload the driver, for example. We don't have support for the ready signal yet, which is part of some protocols, but that can easily be implemented on top by the driver because it's mostly driver specific. It can be handled with the GPIO or GPIO tied or interrupt or something like that. Example normal's SPI slave handler in the SPI driver probe routine, it can set up some stuff and then send messages to the slave. Different APIs, I listed most of them here. An SPI slave handler is really very similar. There's one big difference though, is that if you want to do something, for example, in your probe function yet, you have to use a non-blocking SPI transfer because the probe function should return and the data will not really be sent here. If you want to do blocking stuff, then you have to do it from a thread. And the second big change is that in your remove function, you have to abort anything that has been programmed into the hardware yet. And then, of course, you have to wait for some way for the other threads to complete something like that. Now, on a simple example of this, you have a question?
Yes. You showed at the beginning some 3-wire SPI, so this half-duplex SPI. In that, as a slave, you might get interrupted or you might get a conflict on your master input, slave output. This simultaneously gives the data line. I wonder why we didn't, or you didn't implement an extra callback on the interface to signal that to the upper layer.
Yeah, that's good. I think the 3-wire interface handling it in slave mode is not that simple. And actually, the slave needs to know the protocol and needs to know when it switches from transmit to receive. So
if you know the protocol, you just put different transfers.
Yeah. Then you don't need you don't need the wire because
at any point you might get interrupted. You might get a master trying to writing something on its own on the data line.
Yeah, but master and slave should know what protocol they will have to talk to each other, so else it breaks down anyway. Okay. So back to the example. So I wrote after 3 small examples here. That's the last part. After that, we have the questions. So a first example here is that this is the slave time handler, which will respond with the uptime of the system. So this uses the virtual file in SysFS to convert the slave handler. So you, this time, you write the name of the driver to it. And after that, I used SPI dev test to write some dummy bytes. And in the response, you will see here the uptime in seconds and in microseconds from the remote system. Note that this is the uptime when the previous message was on the other system was received, because it had to. It's not when the master sends a message to the slave. It's the time from when the slave prepared it. This could be used as a simple deadman switch, for example, because if this other remote system dies, then you will no longer receive a valid time, but all zeros or one, or something like that. The second example is a system control handler, which you can use to suspend or resume a system. You just write a specific command to it. The weird hex numbers here are chosen such that I connected some shift registers and a 7-segment LEDs to the bus, so I could see an interesting character on that one, like CZ when you suspend, something like that. And the third example is using SPI dev. If you want more information about the tests, they're at this eLinux.org wiki page. Yes, I did use DT overlays, just for people who are interested in that. And we got this in 4.13. Thank you, Mark. And then I'd like to say what things we could use in the future. More support for other slave controllers. For now, we have Renesas MSIOF, Freescale IMX. More handlers for real-world protocols, perhaps IP networking. Okay, I'd like to thank a few people. So, if we have questions, I think we have 1 minute or something.
So, back in 2016, during Google Summer of Code, there was a project to implement SPI Slave for the BeagleBone Black. Do you know if patches from Renaissance BSP are based on this work, or it's totally unrelated, has been dropped or something?
Yeah, so the question is whether the patches for the BeagleBone Black are related to this. In 2016, they must definitely be newer than the ones from the Renaissance BSP.
Okay.
Because I think those date back to 2014 or something like that.
Some silicon supports other signaling besides the relay, like interrupt. So when the slave wants to transmit something back to the master as well, they use an int line. They have some off-band signaling. Your proposal is also to implement that as part of your driver, right?
Yeah, so the question is about interrupt signals from the slave to the master, that you have to implement them in the driver. Yes, so the idea is that you do that on top.
And technically you would do a write, and during the write you will, or your driver, which is ready to, you would raise the interrupt and wait to start the clock.
Yeah, so if the slave wants to send the interrupt, it can use a GPIO to assert the signal and have to connect it to the interrupt line.
Could you use that slave support to kind of emulate a SPI flash device, so kind of software SPI flash? For example, a use case would be testing, for example, FPGAs or other boards to kind of load the bitstream or other configuration from an SPI, so you can kind of change that quickly without flashing and real SPI flash all the time.
Yeah, so the question was, can you use it as SPI flash? Or I didn't implement SPI flash support because it has an annoying protocol where it relies on the commands that you send in the same message. So you send the command to read data, and then the slave has to respond with data in that same message, and that's not possible. But the SPI flash write you could implement, that's true.
I guess in theory, if you know what this other side is doing, like ignore the make sure that you could ignore the incoming message and then you could know that I just released my FPGA from the internet platform. It will start requesting lots of 4K or
So the question is that you could just ignore the read command and just send data. Anyway, yes, but if you know what in advance what the other side will request, then you can do that. But then basically that becomes part of the protocol.
Yes, but for an FPGA state machine, then it's probably something they're going to do. They're not going
Yeah, for FPGA programming, it's.
So, have you investigated possibility to implement SD card emulation using Slave protocol?
So the question is whether I considered SD card emulation. SD card emulation has a similar issue as reading from SPI flash. So you can access an SD card and treat it like a SPI slave. Well, I'm talking to it, but emulating an SD card, but unless it's just for writing, you cannot do it. You have any more questions? No? Yeah, I think I missed a lot, mixed up the times.